Okay, when using a proof by contradiction, you are going to be using the contrapositive, which is something that I'm putting on your little cheat sheet that hopefully I will have finished and will share with you. But essentially, what the contrapositive is, assuming is putting that the second part of the statement is false. So the first thing is identifying what is being implied, and then assume that the implication, which is the implication is the then statement, is false. So then you're trying to come up with a contradiction, and then that proves that the original statement must be true. So basically, if you assume that both parts are false, and then you end up with something like that's saying like that's impossible, then it shows that it can't be false. So for example, this first one, we have if the integer n is odd, then n squared is also odd. So the implication of this one is that then n squared is also odd. So I'm going to take that section of n squared is also odd, and I'm going to make that false. So the first thing that I'm going to say is let n squared be even. Okay, so once I have made that assumption where n squared is even, thus n squared would be equal to 2k, which is what 2 times some integer k means that it is even. Like that is just the definition that you have to use. So that would mean that n times n is equal to 2k, but this cannot be true if n is odd, because if n is 2k plus 1, then n squared would be equal to 2k plus 1 times 2k plus 1, which yields the result that n squared is equal to 4k squared plus 4k plus 1, which where if you factor out a 2 out of the first grouped terms, you end up with 2 times 2k squared plus 2k plus 1. And since 2k squared plus 2k is an integer, then n squared must be odd. So that would be an example of contradiction, because basically what I got to is I know that the product of two odd numbers is odd. It can't be even. So that's that's the part that reaches the contradiction. I think IB would have accepted it if you had just said, but this cannot be true, and said because the product of two odd numbers is always odd. I don't know that they make you write out the proof, but I thought I would take the time to show you this additional proof at the bottom of why the product of two odd numbers is always odd, just in case. I don't know that IB would ask you to do that, but now you've seen it in case there's a question that asks for you to prove that the product of two odd numbers is odd. So now you know how to do that part of a direct proof. Okay, so that's the first one. Let's look at another example without odd numbers. This is another one that I think you might see occasionally, so I put it on the list, is in terms of rational. So it says show that the square root of 2 is irrational. So in this case, what I'm actually trying to do is, is to show that the square root of 2 is not rational, which means I'm going to try to prove that the square root of 2 is rational, and then I'm going to reach a contradiction. So I'm going to say, assume that the square root of 2 is rational, and then I'll write out what that definition is. So here I say, assume the square root of 2 is rational, or that the square root of 2 is equal to m divided by n, where m and n are integers and do not have common factors. So a rational number, when you think about those definitions of what rational numbers are, they were things that could be expressed as a fraction. And so if the part where it says m and n have no common factors, that means that the fraction has been simplified as much as it can be. Like it doesn't have a common denominator, basically. So that's just an additional piece to say that not only is it a fraction, it's a fraction that has been simplified as fully as it can. Okay, so that is the definition. So if something says proving something is rational, you always have that it's the m divided by n, where m and n are elements of the integers, and m and n have no common factors. Okay, so now I'll proceed with the rest of this particular proof. Okay, So now what I've done is I've squared both sides of my equation. So now instead of square root of 2, I have 2 is equal to m squared divided by n squared. Thus, m squared, I'm just isolating that variable. Thus, m squared is equal to 2n squared. Therefore, m is an even integer because I have that 2 times another integer. I know that that means that that's the definition of even. So m is equal to 2k and m squared is equal to 4k squared, where k is an element of the integers. So now I can rewrite this saying that I know that m squared is equal to 4 times some integer squared, which is equal to 2 times my denominator n squared. Therefore, if I solve this equation for n squared, I end up getting that it's equal to 2k squared, which since I know k is an integer, that tells me that n is an even integer. However, this is where I've reached my contradiction. I'm not going to write all this stuff out if that's okay. This is where I've reached my contradiction because now what I can see is that I have n squared is 2k squared, which has this beautiful little 2 out in front. But I also said that m is equal to 4k squared. Now, if you were to put 4k squared over top of 2k squared, you have a common denominator, you have a common factor. That common factor is 2. But up here, what I said in my definition was m and n have no common factors. So that is my contradiction. Therefore, square root of 2 must be irrational. Okay, I know that this is a lot and it seems extra and whatnot, but the more you do these, the easier they will become. Hopefully this is making at least a little bit of sense. Hopefully it's not just as clear as mud. Okay, a counterexample or a counterclaim is an acceptable proof of the fact that a given statement is false. Normally a problem will tell you, prove that the following statement is false. So that's what the direction said before this one. It says, prove that the following statement is false. And then it says, if n is an integer and n squared is divisible by 4, then n is divisible by 4. In order to prove that something is true, we have to go through a whole bunch of steps. I can't just give one example of where it's correct because that doesn't mean it's always true. That just means it's sometimes true. But what I can do with a counterclaim is I just need to find one instance where it is not true. I can prove that something is false with just one bad example, okay? Like if you're having a debate with someone, if you're arguing back and forth, you can make tons and tons and tons of good points, but you may not convince them that you're right. However, unless you're arguing with someone who doesn't know the rules of arguing, if they claim something to be true and you tell them, you give them an exact example of where it's not true, not something based off of opinion, but something based off of fact, then you have proven that a given statement is false. So let's look at this example. It says if n is an integer and n squared is divisible by 4. So what I'm going to try to come up with is an example of a number. I'm trying to prove that it's not true. So I want to look at this and start here with something that is not the case. So I want a number that is not divisible by 4. So the first number that pops into my head is 6. So if I have 6, which is not divisible by 4, and I square it, for this n squared is divisible by 4, I end up getting that 6 squared is 36. 36 divided by 4 is 9. It is divisible, but 6 is not divisible by 4. Sorry, this little like 7 symbol, that means not. 6 is not divisible by 4. So what I've come up with is a counter example. However, the problem with counter examples is sometimes you can pick a number and it could make it true. So like I could pick a number that's not divisible by 4, and it does work. There could be cases where that is the case. So a number that's not divisible by 4, yeah, I can't think of one off the top of my head. All of my examples are not, but there could be a case where it does work. However, I can prove this statement false because it's not always true. I've given an example where this statement is not true. So that's a counterclaim. Okay, so from here, let's talk about your homework. So I have Rohan and Andrew, you're doing the proof that if m and n are elements of integers, then this equation does not equal 0. So you're going to be trying to prove that one. So you're going to be using a proof by contradiction to solve that. So you assume that m squared minus 4n minus 7 is equal to 0, and then you try to reach something that makes it impossible. Bella and Noxonia, you have this next one, same concept. You're proving that there is no element. So instead, what you're going to try to prove is that there is an element, and then you should end up reaching a contradiction. Same thing for Tomas and Leonard. You're assuming that n is odd, and then you should end up reaching a contradiction. Liz and Jacqueline, you're going to be proving the following statements false, which means that you need to find counter examples for both of these things. So you just have to come up with 2 different examples, like one for each of these, where it's not true. I, again, posted some additional questions to try to get you to practice proof by contradictions or counter examples. So 1 through 9 are about contradictions, and number 10 is all counter examples. 10 should take you very little time in comparison to the other ones, but I highly recommend doing more of this practice, because the best thing you can do to practice these is to just do them. And unfortunately, there isn't delta math repetition that I can give you. So that is your notes and your lesson for today.